integral 4 over, actually let me make it 5 over x squared minus 4. Do you see that? Are you seeing my screen?
Yep.
Great. Okay, so the reason this is a partial fractions problem is some of the other methods don't work, but one of the things you might notice right away is that this is difference of squares on the bottom. And there's a couple of different forms of partial fractions, but we'll just assume for the moment that this 5 over x squared minus 4 equals a over x minus 2 and b over x plus 2. Have you seen this before?
I don't really remember it.
Okay, it's something you already know how to do. This part is not a calculus step over here.
Mhm.
You multiply the top and bottom by the missing thing to make the fractions common.
Mhm.
So and now you just look at the numerator. So 5 equals ax plus 2a plus bx plus 2b. And over here I'm going to write 0x because there is no x term, but this becomes two equations. It becomes the sort of the x equation. That's a plus b, and then the number equation, which is the value of 5 here, it equals 2a plus 2b. Okay, and this is a system of equations. You know how to solve this. You can use any of a variety of methods. Depending on the problem, you may substitute, eliminate, it just depends. We know that a equals minus b. So I'm gonna put that back into this one here. Did I really give you one that doesn't have a solution? I did. Okay, let me change the numbers here to why didn't this one work? Huh. Sorry, I'm just a little bit shocked. So let me change this to let's go 5x up here. And then I think it should work. So let me just slightly change this. I'll grab one from the book for the next one. So this is 5x plus 0, and that just changes these two over here to 5 and then 0. No, that also doesn't work. Okay, let me go back and do one that is given in the problem here. All right. Actually, let me go find a different one. Okay. This is a better example. This will work out nicely. I apologize for that, but the process is exactly the same. So when you have an integral that doesn't work with the use substitution, like when you take the derivative of the bottom, 2x minus 1, it does not become the top. You're drawn towards like, okay, it must be partial fractions, so that you have to immediately factor the bottom is the most common situation here. So again, it's you set the numerator, well, over the denominator. We'll show it in factored form here, but this equals a over x minus 3 plus b over x plus 2. And then just like in the previous example, you multiply the top and bottom by the missing thing here, missing term in this case. So you have 3x plus 11 equals ax plus 2a plus bx minus 3b. This is probably clearer anyway. So you set the x terms equal. And there's actually a few other ways to do this, but this is the most straightforward. 3x equals ax plus bx, but then you eliminate the x. So you just make this, you transition this to 3 equals a plus b. Then the non x ones become 11 equals 2a minus 3b.
Yep.
This one, we'll just multiply the first equation by 3. So that gives you 9 equals 3a plus 3b. You add the equations, 20 equals 5a, a equals 4. And then you go back like maybe to this line right here. 3 equals a plus b, 3 equals 4 plus b, so b equals -1. This is not the calculus. They actually teach this in pre-calculus, but you wouldn't have spent very long on it. So
Mhm.
the integral itself, though, you transform the entire integral back to this a, which is 4 over x minus 3, plus, and then your b is -1 over x plus 2. So just to be clear, this boxed thing is transformed into this.
Mhm.
The calculus is very easy in this because these are almost always natural log absolute values. And then you bring that coefficient out in front. And then a plus c. So almost, I would say the bulk of the work is over here on the right, is to find these a and b's. And on your exam or quizzes, sometimes they just ask you to find a and b or set it up. They don't actually want you to integrate because it's fairly straightforward to do that.
Okay. It's a lot simpler than it
Yeah.
looked.
Yeah. And the reason this one didn't work is this one actually is a known integral, and that's why it didn't work out. It's an arctangent. So let me just see if you have any others here that are like that. I thought maybe you had an initial value problem like that on here, but doesn't look like it. Actually, you kind of do here. So can we move to initial value problems, but we'll do the same kind of thing here that we just did?
Sure.
All right. So an initial value problem means that you're solving for the constant of integration in most cases. So what is on the left here is called a differential equation. There's entire classes in this. The one we're looking at is called separable. And that means you can separate the variables. This here on the right is the initial value. It's typically at 0, but it could be at another number. And you use this to determine C, the constant of integration.
Mhm.
Another thing here is that this one's in terms of T instead of X. That's a small change. That just means your independent variable is going to be T instead of X. So because it's separable, you need to move the Y terms left and anything else right. And the only way to move terms in these types of problems is to multiply or divide. You almost never add and subtract, almost never. So the way this looks is you divide both sides by this y times 1 minus y. And then you're not exactly doing this, but you multiply both sides by dt, and that cancels that out.
Mhm.
So the net result here is you have the integral of 1 over y, 1 minus y, dy equals the integral of, when you divide this, you get 1 dt. Have you seen any of this before?
A little bit, yeah.
Okay. So the reason I chose this is I wanted us to do the partial fractions on the left here. The integral on the right is just power ruler. It's just t. That's something you've seen before. But on the left here, this is partial fractions.
Mhm.
Okay, so we have 1 over y times 1 minus y equals a over y plus b over 1 minus y.
Mhm.
So to do this correctly, you multiply this by 1 minus y, the a, top and bottom, and then on the right here, the b by y, top and bottom, because you have to get the same denominator.
Yep.
1 equals a times 1 minus y plus b times y. So there is no y term here. So you could write 0y plus this if that was helpful. Do you want to try solving for a and b, or do you want me to continue working this out?
I can try.
Okay. You'll find that the answers are pretty nice here. So I'll check back here in about 60 seconds.
Okay.
I'm going to write out some steps. So the correct answer is that both a and b are 1. Let me know if you have any questions about how to do that.
Don't have any questions.
Great. So this integral right here on the left, I know I'm sorry for moving around on the screen, but just to kind of keep in line with all this, is the integral becomes 1 over y plus 1 over 1 minus y dy. This one on the left is that special case. It's the natural log absolute value of y. This one on the right is the natural log of the absolute value of 1 minus y. But because of this inside here, this is actually u substitution, and it ends up being there's a negative that comes out as a result of that. Another way to kind of work through that is if you were to take the derivative of this, it would be 1 over 1 minus y. But when you take the derivative of the inside function, there's a negative, and that negative cancels out to make a positive.
Okay.
Okay. We're not going to carry through the rest of this problem quite yet, because I want to do a couple more initial value problems just to like get your comfort level with them, and then we can solve, because we need to solve for the constant of integration. And depending on the problem, it could be quite a bit of work here. So I'm going to just restart a new question, if that's okay with you.
Okay.
All right. So this one is an initial value problem. You'll notice they give you it at 1 when x equals 1, not at 0. That's okay. There are no y terms here, so you don't have to move anything left. You generally keep, it's generally integral of something dy equals integral something dx. And your dy is on the left. You move the dx over. And so this is the new problem that we're going to solve, this, or new kind of integration. On the left, it's just y, no big deal. On the right, though, and this is why you learned all those techniques, I'll even add this as a 0th step. You can rewrite it. You can, it's a known one. There's u subs, all that stuff here. Does anything stand out with you about how to integrate this thing on the right.
I mean, it might be pretty easy to use up at the middle portion.
That's the direction you would go because it's in parentheses, it's squared. The problem is when you take the derivative, it's just not there. So this is actually a rewrite, and you just expand the binomial. You just take x plus 1 over x and multiply it x plus 1 over x, and then you integrate.
Mhm.
So this becomes x squared. X times 1 over x is 1. 1 over x times x is 1, so that's plus 2. And then what am I missing here? Plus, actually, let's do that differently. Let's go plus 2 plus 1 over x squared dx. And then this is these are all power rules when you integrate. So it's 1/3 x cubed plus 2x minus x to the minus 1 plus c.
Mhm.
Our initial value was this y of 1 equals 1. And this is what allows you to solve for c. So you plug these in for y and then for x.
And then you just solve for C.
Exactly. And it could be nice, could be not nice, no idea. What do we got? 1/3. 2 minus 1 is 1, so that's 4/3. So it looks like c is like negative 1/3. And then your final step is you do want to rewrite it with that new c.
Okay.
All right, let's, okay, if I have you try one here.
Yeah, that's fine.
This one has the appearance of being really complicated, but you do know enough to do it. And I'll just give you a minute here to see if you can start working it out. Let me know if you have any questions.
Okay.
Hey, Natasha, how are you doing on this one? Sorry about that, if you can hear that.
Fine.
Sorry, there's two there. So this one is this is a known antiderivative.
Mhm. Just trying to find that.
Do you still have it? Do you still have that table pulled up from the last
Yeah, I do.
lesson? Okay, so this one is cosecant u. But then you have to put a negative in front. So let me show you here, and then we have to deal with the two theta. So if we were to make a u substitution here, you would probably see it more directly. So it ends up being minus cosecant u, but u is really 2 theta. But because of the fact that there's a 2 inside here, you have to multiply by 1/2.
Mhm.
And then plus c. So now that we have this part, you have to use your initial value, y of pi over 4 equal, what did it say, 1 or -1? Okay, so that's 1 equals minus 1/2 cosecant 2 times pi over 4 plus c. How is your unit circle knowledge?
I don't know cosecant off the top of my head.
Yeah, neither do I. We're on the same page there. Cosecant though is 1 over sine. And sine of pi over 2 is right up here at the top. So the y value there is 1.
So it's 1 over 1, so it's 1.
Yep. And then times 1/2, so you got 1 equals minus 1/2 plus c. C equals 3/2. So you go back and you rewrite this line, but you plug in for c.
Okay.
So these really aren't any different than the previous problem. You may have to make one algebra step to like move it around one side or the other. They do rely on you to know your integral tables, maybe use substitution, but they're really no different than just me straight giving you an integral like we've done in a few different problems.
Mhm.
Okay, we can move on to slope fields, if that's okay.
Yeah, that's fine.
All right. So there are a couple of different problem types that you might see for slope fields. The first one is where they give you a differential equation, and then they ask you to create the slope field. So let's just say dy dx equals -x. This is a differential equation on the left here, but the way you would read it is the slope is minus x. Okay, so there's a couple of slopes that you know really well, like a slope of 0 is a horizontal line. Slope of 1 is a line up and to the right. Slope of -1 is a line down and to the right. Now the mistake here is to just plug in points, because you just have your differential equation in terms of x, not x and y. So like, for example, right here, this dotted line, this is where x equals 1. Every point along here is where x equals 1. When you put 1 into x, what is the slope?
It's -1.
-1. So it's this. You draw these lines here. Then you choose x equals 0 or x equals -1, however this ends up working out. But you plug that back in and you find, for example, at 0, the slope is 0. So you just draw these horizontal lines. Similarly, at -1, when you put it in for -x, it becomes +1, up and to the right, up and to the right, and so on. This is not a complete picture, but it's usually the kind, I just grabbed it out of the book that you sent me. Like, they just usually want me to give you a few grid points. Okay, so let's try another one here that's slightly more complicated. dy dx equals 1 minus y. And this time, kind of the same grid. So there's, when it's only in terms of one variable, you generally like want to use the ones that are the same everywhere. So we want to look at the case when y equals 2, y equals 1, y equals 0, and then y equals -1. And the most useful slopes are the 0, 1, and -1.
Mhm.
So do you feel like you have enough here to give this a try, or would you like me to work through one more?
I can give this a try.
Okay, very good. I'll stand by. I'm going to jump in here and just start drawing some of the lines. And if you have any questions, let me know.
That's pretty much what I got.
Perfect. What they're grading for is the general direction and then the steepness relative to like the previous line. They just want to see that that's steeper than the one before it.
Doesn't necessarily have to be accurate.
No, it's these aren't designed for that. They're designed for like these are supposed to be done on computers. So it's you know, it's always it's always you know, a little odd when we're trying to do things that are meant to be done by computers, but you know, there's a few examples we can do by hand. So the last type we'll talk about is let's say dy dx, and we'll include both variables this time. Let's say it's 1 over x minus y. And this time, keep in mind, there's just literally there's an infinite number of these that could be possible. So just like we're just doing the bare minimum here. So when you have two variables, like one approach, and this is the slow approach, is to at every point put the values in to the equation. Like if you had unlimited time, this is what you would do. It doesn't work very well though, because if you have a bigger one, it could take you a long time to finish. So the second strategy is to like look for kind of the same stuff we talked about in the previous problem. Is look for places where the slope is 0 or 1 and -1. So for example, when x is 1 more than y, like when x is 2 and y is 1, the slope is 1. Okay. Well, like what is that? Well, it's really when x equals 2y. I'm sorry. When x equals y plus 1. So where is that line on this? Well, if you change around, it becomes x minus 1. So it's through here. And we can test these points. Like, is that 1, 0? Is 1, 0 make this 1? Yes. When x is 1 and y is 0, it becomes 1 over 1 minus 0. How about down here at 0, -1? Same thing. It works out to be 1. Another thing we can look for is undefined. And that makes more sense here. So when x equals y, this thing is undefined. Undefined slope is up and down. So along the line x equals y, which is here, we get a completely vertical slope. And the idea by doing it this way is you hopefully get a little more
It's a visual way of saying it.
yeah. So the rest of the points you'd have to try yourself. So I don't expect you to get something like this. So I'd like to move on to the next type of problems, which are matching.
Okay.
And they're going to be more difficult in some ways because they give you more to look at. But what we're going to do them is one at a time here. And I apologize if you've already done these in the practice, but these are really hard to come up with on the fly. Like if this were, say, an algebra 1 class, we could just kind of figure them out here. So I could make up new ones, but these are a little bit tougher to do. So kind of like the last one, you want to look for like things that are unusual, like where's the slope undefined in this one? It's undefined.
X equals y.
Minus y this time.
Y.
So that's this line. So when we look at like kind of go from top left to bottom right, we're looking for the one with completely vertical lines along there, so these aren't scaled, right? This one kind of has it. Let me see if I can. Oh boy, that's really bad. This one I think has it here. So that would be one possible way of like figuring out that letter B is correct. But it's more of a matching exercise. It's more like, well, it's not A, it's not C, it's not D, so it must be B. Now that one wasn't great. I apologize. Let's look at like 41 here with a new set of questions here. All right. So this time, X and Y are on top. Okay, and here we're generally interested in like where the slope is equal to 0, and this is the slope. So it's 0 when either X is 0 or Y is 0, or both. So this has horizontal lines when X is 0 or Y is 0. So along the axes, so like see how this an A has horizontal lines, and we presume that does as well. But so does C. So now you, as a student, have to figure out, well, is it A or C? And you have to say, well, what's different between the two of them? And so, these are out. And then if you could look at those, what do you notice, or what might help you figure out which one is the correct answer?
A has negative slopes in positive quadrants.
That's right.
And it's reversed, and C does not. It's the opposite.
So A slopes here are negative. I think that's what I heard. They're going down, and then C's are positive. They're going up. So this is where it is okay to test a point, because you're comparing between the two. So if you pick a point like 1, 1 in the first quadrant, well, here it's negative and here it's positive. So therefore it must be C. And that is generally the approach here that you're going to see for that. Do you remember what kind of slope field questions you got on a test or a quiz, or is it anything?
Was kind of the same stuff.
Okay. These are not covered on the AP, by the way. So there's like use substitutions aren't covered on it. Integration by parts is not covered on it. So some of these topics are just, they're part of the B course, part of the course where you pick them up again in BC.
Mhm.
Or if you're going on to the university, you do them in calculus too. All right. Ready to do some Euler's method, or is there other things you would like us to look at?
I'm good at Euler's method.
So a couple problems here for us to look at. All right, so Euler's method is a recursive method, and you must start with a differential equation. You must start with an initial value, and you need to know what you're incrementing to. So you're starting at x equals 1, and then you're moving up to like x is 1.1, then 1.2, and then you stop when it's 1.3. So the output of this, let me see if I can find one so you can see like what this looks like when you're done, and then we'll work backwards to calculate it. So I'll snip this in here shortly. 1, 1. Let's go 10 partitions. See if that works. Oh, xn is 2. We do that again one more time. Okay, so what your instructor is looking for is this is your final answer. This right here. They want to know at each x value, what is the f of x value. So you already have the first one, like it's given here. Okay, so the way this works is they use subscripts. They say the y next, which we'll call I don't know, let me call this 0, step 0. So y1 equals y0 plus, and then you're evaluating the derivative at x0 and y0, and then you're multiplying it by your delta x. You may have seen a slightly different notation on this. Let me pull up another possible way you might have seen it. This may be more confusing than not, but so the y0, hopefully that's same. When they say f, they're referring to the differential equation. That's dy dx, and then t1 minus t0. Think of it as like 1.1 minus 1. So this tends to always be delta x. All right, so now to actually do some things here. So y1, that's what we're trying to find. Y0 is the previous one, so that's 1 plus, we evaluate the derivative at the previous points, 1, 1. So we're evaluating it at 1 plus 1 minus 1. Our delta x is 0.1. So this simplifies to 1 plus 1 times 0.1, which equals 1.1, and that's right there. Okay, so then the next one, and you don't have to keep using the subscripts, but the next one is y1, so our previous answer, plus, now we evaluate the derivative at these new x and y values. So that's 1.1 plus 1.1. I'm plugging them into this equation up here, minus 1 times delta x, which is 0.1. 2.2 minus 1 was that 1.2. Y1 is 1 and then 0.1. And I'm just going to, so that was that 0.12, 1. I messed, oh no, it's 1.1, not y, not 1. It's 1.1 plus that equals 1.22. You get that line right there. And then y3 is y2 plus, and you evaluate your derivative at the previous point. So at y1 plus, I'm sorry, y2 plus x2 times your delta x. So our y2 is 1.22 plus your derivative, which is x plus y. So we go back to our table from the previous line, 1.2 plus 1.22 times 0.1. And you generally get a calculator here. Did you have a calculator section of your exam?
Not for the most recent test I took.
Okay. Did you have this on there, or was it, are you still in the middle of it?
There was Euler's method on there.
Okay. All right. We can do another Euler's. That's the final answer, by the way. We can do another Euler's problem if you would like. There's another one in the book you sent me, or we can do another topic.
I can move on to another topic. I understand Euler's method pretty well.
Great. All right. So we should have done a question like this with slope field. So I'll just briefly touch on it. So they sometimes want you to sketch the solution to the slope field. And it's just connecting like lines, but they want the one that goes through 0, 0. So it has to go through that point. So like what I see, and I'm not saying this is perfect, but this is kind of what I see here, is something like that. It's literally just connecting the points that are within reason. If you saw a slope field for like X, where the solution is a quadratic, you would see, like, think of a quadratic here, but now if I just graph the parts of it that are curving,
yeah,
like you have to be able to kind of visualize and see that. So that's another kind of slope field problem. All right, so the next thing that they show here, which I think is kind of worth talking about, is they give you what's called a second order differential equation, but it's linear, and you know how to solve this. You have all the tools to be able to do that. So there's this discussion that happens early in the course where they say, okay, this is the position of a particle, and they give you some function. And when you take the derivative of position,
you get the velocity.
you get the velocity, which we write as v of t, or we say velocity, but it really is s prime of t, or ds dt, if you prefer. And then when you take a second derivative, it's ds squared over dt squared, or d squared s over dt squared, and that's acceleration of t. So now that you know about integrals, you can go backwards. So we're going to integrate both sides of this. So on the left side, when you integrate it, you get ds dt, or you can write v of t. But on the right, this is power rule. It's 2t plus 3t squared plus c. This right here is an initial value. This says that when t is 0, velocity is 4, v of 0 equals 4. So 4 equals 2 times 0 plus 3 times 0 squared plus c. And you get that c equals 4. So your v of t is now 2t plus 3t squared plus 4. Now, if you integrate velocity, what do you get?
You get position.
Position. Okay. So one of the questions I could ask here is like, how far did it travel in the first second? And what I'm literally asking you to do is integrate from 0 to 1 v of t dt.
Mhm.
But I won't show this. I'll just ask this written question that'll say, what happens. So to do this, you substitute in your v of t, 2t plus 3t squared plus 4 dt. Okay, and then you find your antiderivative. And then you evaluate it from 0 to 1.
Which is 6.
Something like that, yeah. Now, I could alternatively ask you for the position function. I could say, what is s of t if s of 1 equals 12? So this is totally unrelated to what you just did. It's just like that's another fork or another spin-off on the same question. So position is the integral of v of t. And we already did this. It's the integral 2t plus 3t squared plus 4, but this time there's no bounds of integration.
Mhm.
It's the same antiderivative
Plus C.
plus c, but now we use the initial value to solve for c. So 12 equals 1 plus 1 plus 4. And that means that c equals 6. So s of t equals t squared plus t cubed plus 4t plus 6. And so if I asked you a question like interpret s of 0, which ends up being 6, I'm asking for a meaning of that. And you would say something like the particle started 6 away from the origin.
Mhm.
I could ask that. And this is more, just by the way, this is more of your AP style question that we just did.
Yeah.
You've probably done some free response for this A, B, C, and D. So just, we're about to close out here. I know you didn't ask, but my opinion is it sounds like that you're understanding what I'm doing here today. If that's the case, there's no reason you can't do well in the AP with just a little bit of kind of a push here the next month or 6 weeks, whenever the AP is. Like, if you're understanding this, I think that's still possible, a realistic goal for you.
Okay.
Well, thanks so much for scheduling. I've already sent you the notes from the first hour. I'll send you the notes from the second hour here shortly, and be happy to help again.
Thank you.
Have a great night. Bye now.
Bye.